This line point at 2, 3 has absolutely zero length and zero width. How many dimensions does it have? I bet you're inclined to say 0 because of it having no length and no width, but it's actually two-dimensional despite not showing it. So if a point can have no length, no width, no nothing, and still be two-dimensional, what exactly does it mean to be zero-dimensional? By the end of this video, you'll not only understand what lies before dimensionality, but you'll also get a rare glimpse into what the smallest thing actually is. It's not a point. Why did that dot feel like a zero-dimensional object, even though it was clearly sitting in 2 dimensions? We tend to tie the idea of a dimension to the object that visually appears, rather than to the space that the object exists in. So, when we saw the dot on a 2-dimensional graph, we should have recognized it as a 2-dimensional object. But the moment we noticed it had no length and no width, our intuition broke. We subconsciously treated those missing properties as if they removed the dimensions themselves.
This mistake is what I call the suitcase fallacy.
The suitcase fallacy happens when we confuse the thing with the setting that makes the thing possible. The dot itself didn't suddenly gain dimensions. What changed was the context it was placed into. But visually, those two ideas collapse into one another because the object and the space show up together. Our intuition quietly stuffs the space into the object, as if the dot itself were carrying its dimensions around, like clothes packed into a suitcase. And that's why the dot felt zero-dimensional, even though it never actually was. So the next question becomes, if a point, shape, or object doesn't possess dimensions, where exactly are the dimensions coming from? A dimension isn't a property of the object, it's a property of the space the object exists in. A dimension is simply a way measurement is allowed to vary, a direction in which things can be compared, separated, or constrained. That means objects don't generate dimensions, they're inserted into them. And once you see that, a point stops looking like the smallest thing that exists, because it's already sitting inside a structure that had to exist first. Think of a dimension like a cylinder of a revolver. The cylinder is a space that can hold many distinct bullets. Each bullet fits into it, but none of them contain the cylinder. The bullets are like mathematical objects. They could be points, squares, spheres, anything at all. And just like bullets come with a revolver attached, mathematical objects don't carry the space they appear in as part of what they are. The space exists first. The objects are what get placed into it. What space gives an object isn't shape. It gives it freedom. For every space, 1D, 2D, 3D, and beyond, we gain an additional degree of freedom. A degree of freedom is just an independent way something is allowed to vary. In a 1D space, variation is locked to a single direction. In 2D, variation splits into 2 independent directions. In 3D, we add depth, a freedom that simply didn't exist before. And crucially, these freedoms don't belong to the object. They belong to the space the object is embedded in. The spaces themselves are what mathematicians call manifolds. The word comes from a root meaning variety, and that's exactly the right intuition. A manifold is a container of allowed variation, 1 dimension, 1 degree of freedom, 2 dimensions, 2 independent freedoms, 3 dimensions, 3. Objects don't dictate these freedoms, the manifold does. A 2D manifold can't express depth, so when a sphere is placed into it, all we ever see is a circle. A cube becomes a square. No information is destroyed, it's just inaccessible, because the space doesn't have enough degrees of freedom to reveal it. But now watch what happens in reverse. Take a square, perfectly flat, and place it into a 3D manifold. The square does not gain thickness, it remains entirely flat, but it now exists inside a space with 3 independent degrees of freedom. So under the definition we're using here, it's a 2D object embedded in a 3D space, and its dimensional context is 3-dimensional. And all of this matters for one reason. It tells us that the dot was never carrying its own dimensionality in the first place. A point on a 2D graph has no length and no width, yet it can move freely, left, right, and up, down. Those freedoms don't come from the point. They come from the 2D manifold it lives in, which is why that dot, despite having no size at all, is still unambiguously two-dimensional. So what's left of the point after we strip away the 2D manifold it's sitting on? This is the heart of the question. Up to now, everything we've been working with has been a mathematical idea rendered as geometry. And the moment we remove the manifold, the dot just vanishes, because seeing itself requires space. So I guess with nothing left to see, I can just end the video here. Goodbye. Wait. But maybe there is something left. I thought we just phased out of math into pure nothingness. So, what is left? Well, what's left isn't some dot on a graph. That would still require it to be somewhere. What's left is an object with 0 degree of freedom, something that can't vary in any way at all. It has no possibility of change. This is the 0th dimension. Now, this is a crazy thing to try to picture because it is quite literally unpicturable in the truest sense. This is the point with 0 dimensions, and I deem it the point core, the pure essence of a point, whose immutable characteristics cannot be further reduced. The immutable characteristics are identity. The point core is what it is, and it isn't what it isn't. When dimensions are added, it stays a point and doesn't change into something else. And non-variability. The point core cannot vary. When dimensions are added, it stays a point. So we've arrived at what truly is the edge of math, not by expanding it, but by looking beneath it. And that's the significance of what we just did. We uncovered the smallest thing that can mathematically exist, the point core, smaller than that infinitely small point that we started with. And the deeper takeaway is this: when we ripped that point off the graph, it didn't just collapse into nothing and phase out of existence. It allowed us to see a deeper structure underneath the math that wasn't even mathematical, it's purely structural. And that's a really unique thing to get to see. Thanks for watching.